So far, we've talked about the concentration of H3O+, OH-, as well as pH and pOH. What I'd like to focus on this slide is remind you how to convert between all four of these parameters. The good thing about it is it's actually quite simple. The starting point for this is the autoionization of water. So as you might be aware, pure water will self-ionize into H3O+ and OH-. Based on this equilibrium reaction, we can write an equilibrium constant, and we can do this for any type of equilibrium reaction. Our equilibrium constant is represented by the symbol K, and since this is a special equilibrium constant specifically for water, we give it the symbol Kw. So for any equilibrium constant, the expression can be written as the concentrations of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants, also raised to their stoichiometric coefficients. So you see here that the good thing about most acid-base reactions is the stoichiometry is all 1-to-1. Okay? And on the product side, we have H3O+ and OH-. So our expression for Kw is going to be Kw equals the concentration of H3O+ times the concentration of OH-. Now normally we would divide by the concentrations of the reactants, but what you'll notice here is that the reactants are pure liquids, and whenever you have a pure liquid or a pure solid, you do not include it in the expression for the equilibrium constant. So in this case, Kw equals the concentration of H3O+ times the concentration of OH-, and that is the complete expression. The value for Kw is 1.0 times 10 to the negative 14 at 25 degrees Celsius. So this part here is actually quite important because equilibrium constants are a constant with respect to concentration. However, they can change with temperature. So getting back to this expression, we can rewrite this expression in terms of H3O+. So dividing both sides of the expression by the concentration of OH- gives us H3O+ equals Kw divided by KOH. Similarly, we can write that expression in terms of OH-. So in this case, we would want to divide both sides of the expression by the concentration of H3O+. And in doing that, we get the concentration of OH- equals Kw divided by the concentration of H3O+. Okay. The next step. So this is how we convert between the concentration of H3O+ and the concentration of OH-. The next step is we can look at this equation here for Kw in a slightly different way. And in doing so, we might want to take the logarithm of both sides. In fact, we actually are going to take the negative logarithm. And because we're doing the same thing to both sides, the equality here doesn't change. So the negative log of Kw is negative log Kw, and on the right-hand side, we have the negative log of this times this. Now, the nice thing about logarithms is when you multiply inside a logarithm, that's just like adding logarithms. So we have negative log of Kw equals the negative log of H3O+ minus the log of OH-. So you might be familiar with this. This is just a term for the pKw. Remember, P just means negative log. This is the pH, and this is the pOH. And because the negative log of 1 times 10 to the negative 14 is 14.00, then we get this expression, pKw equals pH plus pOH equals 14.00. The last step here is just to rewrite this expression in terms of pH. So here we're just going to subtract pOH from both sides, and this gives us pH equals 14.00 minus pOH. We can also write an expression where we solve in terms of pOH, and in this case we'd subtract pH from both sides. So this gives us pH equals 14.00 minus pH. So what this tells us is if the concentration of H3O+ increases, then the concentration of OH- decreases. Similarly, if the pH increases, then the pOH decreases, and vice versa. The last important point from this slide is that these four equations tell us how to convert between H3O+, OH-, pH, and pOH. So the take-home message here is if you know just one of these parameters, you can calculate all three of the other ones, which will be very useful for solving equilibrium questions or problems. At 25 degrees Celsius, Kw for water equals 1.0 times 10 to the negative 14. And therefore the pKw, which is just the negative log of Kw, equals 14.00. Under these conditions, the neutral point for water is pH 7. At pH 7, there's an equal concentration of H3O plus and OH minus. That's what's meant by the neutral point. Below pH 7, our solution is acidic. And under this condition, the concentration of H3O plus is greater than the concentration of OH minus. When the pH is greater than 7, the solution is basic. And under this condition, the concentration of H3O plus is less than the concentration of OH minus. Keep in mind that these things are true only at 25 degrees Celsius. Why is that? Well, this is because Kw is temperature dependent, right? Kw equals 1.0 times 10 to the negative 14 at 25 degrees Celsius. But what about the other temperatures? Well, at 0 degrees Celsius, Kw equals 1.5 times 10 to the negative 15. And therefore, the neutral point at 0 degrees Celsius is pH 7.41. At 50 degrees Celsius, Kw equals 5.5 times 10 to the negative 14. And therefore, under this condition, the pH is neutral at pH 6.63. For those of you that have trouble converting between pH, POH, H3O+, and OH-, this pH box diagram can help to show you the equations you'll need to do any conversion between those four parameters. So for example, to convert between pH to POH, we can see that all we have to do is subtract 14 from the pH to calculate the POH. Similarly, to convert between H3O+ to OH-, we see that all we have to do is take the Kw and divide it by the H3O+ concentration. Now, to convert between H3O+ to POH, we can see that we have two options. We can either first convert to the OH- and then convert to POH, or we can convert first to the pH, and then from the pH we can convert to the POH. Now, in either case, you'll take two steps. However, in practice, it's usually easier to convert between pH first, because this last calculation is simply a subtraction, which is a slightly easier calculation than doing a division or a logarithm.